One major application of the optimization techniques we have so far is the idea of regression. We're going to look in particular at linear regression, which means the idea here is that we take a bunch of data points, x1, y1, x2, y2, up to xn, yn. Now, these are not variables. This is actual measured data. So we don't know necessarily that these even make a function. But we're going to take these data and we're going to try to come up with a, in this case, a line, ax plus b, that is sort of the best fit line for this set of data. So if we were to just make a sketch of what's going on here, we've got this collection of data points, and we have this line that hopefully in some way minimizes the error between the line and the data set. So if you look at the error between any one point in the data set, if we zoom in on this section right here, you have your point, which is some x value, y value, and we're going to look at the point that goes straight up or down that's on the line. So this is xi. Now it's on the line, y equals ax plus b, so I'm just going to plug the x value into the line, and we get a xi plus b. So if you look at this distance here, the actual error, this ith distance is the absolute value of axi plus b minus yi. So that's the error in one of these pieces, and we're going to take the total error. Now, for the optimization techniques we have, optimizing an absolute value really doesn't work so well. So we're going to look at something called the root mean square error. And what this is, what we'll do is we'll take the individual errors, square them, add them up, and take the square root. So this is the root mean square error. And we want this thing to be minimum, because we want the line to be sort of best fit to minimize this error. Now, minimizing a quantity is the same thing as minimizing its square, because square is an increasing function. So we can instead look at the error squared, which is the sum of the individual distances squared, and we want this to be minimum. So let's actually plug in the formula we have for distance and see what we have. So this is going to be the sum, I goes from 1 to n. The individual distances squared, so axi plus b minus yi squared. We want this sum to be minimum. Now remember, the x's and y's are not variables, they're data, they're measured data, so we have no control over the x's and the y's, but we do have control over a and b. So here the a and the b are the variables, where the x's and the y's are constants, those are fixed data. So now to minimize or maximize something, we want to take the gradient and set it equal to 0. So since a and b are the variables, this gradient vector, remember this means the partial with respect to the first variable and the partial with respect to the second variable. It means we're going to take the partial with respect to a, set it equal to 0. So the partial with respect to a here is going to be the sum, I goes from 1 to n. Well, we've got a power rule first, so this is 2 axi plus b minus yi times, by the chain rule, the derivative of the inside is xi, and this is the partial with respect to a, it had better be 0. Likewise, we can take the partial derivative with respect to b, so we'll go through and do the same thing. First we take care of that outer function, axi plus b minus yi, times, now the derivative of the inside with respect to b is just 1. And we need this to be 0. So now let's take this system of equations and see if we can solve this for a and b. If we go and simplify the first one, for starters, we can divide both sides by 2, just to get that 2 out of there. And the second equation, we can do the same thing. We can divide both sides by 2, simplify things a little bit. Now if you look at the first equation, we can distribute the xi through and break that sum apart. Say that this is going to be a times the sum, I goes from 1 to n, of, now the a term has xi times xi, so that's xi squared. If we look at the b term, again we distribute the xi through, this is the sum, I goes from 1 to n of xi. And now the y's don't have any b's on them, so we'll move those, a's or b's, so we'll move those to the other side of the equation. And we have over here the sum of xi yi. And again, I goes from 1 to n. So that's our first equation boils down to this one. Now, since the x's and the y's are just data points, this quantity right here, it looks complicated, but this is just a number that we get from the data. And the same goes with the sum of the xi's. This is just a number, and this is just a number over here. Now we can do the same thing in the second equation. We take that a out, break the sum apart. This is the sum I goes from 1 to n. The only term we have in there that involve a's are the sum of the xi's. If we look at the b term, this is just the sum of 1, because there actually are no variables here. And then on the right-hand side, we move the y's over, and we get I goes from 1 to n of yi. So now this is actually a system, two equations and two unknowns. The a and the b are the unknowns. So we can actually solve the system using matrix methods. So this, if we were to take this, turn this into a matrix, the first entry of the matrix is the sum of the squares of the xi's. So if we treat the xi's as the components of a vector, the first entry is the norm of x squared, if we think of x as a vector. The b coefficient is the sum of the x's. And on the right-hand side of that first equation, we have the sum of x1, y1 plus x2, y2 plus x3, y3. And that's just the dot product of x and y treated as vectors. And then we do the same thing on the second equation. We have the sum of the xi's. This last one, if we add up 1 n times, that's n. And then we'll sum up the y's. So this right here gives us a system of equations that we can solve for x and y. And that gives us the line that minimizes the root mean squared error to the data items. Now there's nothing stopping us, nothing preventing us from stopping at a linear approximation. We can look at a quadratic that best fits the data. So again, now usually what you would do is graph the data and see what it generally looks like. So if we think our data looks like a parabola, maybe, make that thinner a little, maybe it would be better to come up with a quadratic that fits your data. So you can do the same thing. You take your xi, yi, you take your data set, and say I want to approximate this with ax squared plus bx plus c. So maybe this would be a better fit depending on how the data looks. And you can go through the same methods. If you look at your individual distances, if we zoom in on a part here on our curve, so this is the point xi, yi. And this on the curve is the point xi, and then we're going to plug that x into the function that we have. So axi squared plus bxi plus c. And if we look at the distance, well, the x's are the same, so those don't contribute to the distance. So this is just a xi squared plus bxi plus c minus yi. And then we can plug this into our root mean square error formula. So that we know that our error squared is going to be the sum, I goes from 1 to n, of our distance squared. So this gives us a xi squared plus bxi plus c minus yi, all squared. And we want this quantity to be minimum. And now remember, the x's and the y's are data, so we have no control over those, but we can control a, b, and c, so those are the variables. So a, b, and c are the variables. So that means our gradient will be the partial with respect to a, partial with respect to b, and partial with respect to c. So we'll set this vector equal to 0. So if we look at the a partial with respect to a here, let's maybe look at another page. So if we take the partial derivative of this with respect to a, we've got the sum, I goes from 1 to n. And then we take care of the outer function first. So we've got 2a xi squared plus bxi plus c minus yi times, now the derivative of the inside with respect to a is going to be xi squared. And we need this a partial to be 0. Right? This was our partial with respect to a equation. And we take the partial with respect to b. We've got the same thing. We go and take our derivative here. This still gives us a sum. I goes from 1 to n. We take care of the outside function first. So this is 2 axi squared plus bxi plus c minus yi times now the derivative of the inside with respect to b is xi, and this derivative has to be 0. And we do the same thing with the c partial. If we take the partial with respect to c, we've got the sum I goes from 1 to n. We take care of the square first, so the sum of axi squared plus bxi plus c minus yi. And now the derivative of the inside with respect to c is just 1, because we have no coefficient here. And this has to be 0. So now we do the same trick we did before. We're going to rewrite this as a system of equations. You take your first equation. The a coefficient is the sum of xi to the fourth. Right, we distribute this through. This is after canceling the 2, of course, like we did before. So we've got axi to the fourth. We've got b times the sum of xi cubed. C times the sum of xi squared equals, and then on the right-hand side, we're going to move this y term over, and we've got xi squared yi. Our second equation, we can do the same thing. We distribute the xi through, and we've got a times the sum of xi cubed, b sum of xi squared, c times the sum of xi equals, and then on the right-hand side, xi yi. And then finally, we can do the same with the last equation, with our c equation. And this gives us a times the sum of xi squared, b times the sum of xi, plus c times n, because here we have no x's, and then on the right-hand side, the sum of the yi. And again, since the x's and y's are just data, this gives us a 3x3 system of equations that we can solve for a, b, and c, and that'll give us the quadratic that minimizes the root mean square error. And hopefully you can see how this generalizes to higher dimensions to arbitrary polynomial approximation. So this is the one big application we can do using optimization techniques.